I have a long-standing interest in the teaching of science and in how people learn science, and that means that I have a particular interest in science museums and exploratoriums and informal centres where children can go to learn science. But although I find them fascinating, I'm always a little puzzled by what's going on. The designers of science museums, exploratoria, things of that sort where there are practical experiments, have obviously got something in mind when they create all those wonderful things with handles to turn and buttons to press, and you can see science in action. And I go around and I look at what children are doing there, and it's a puzzle to me whether they're actually learning any science. I can see they're having fun. I can see that the toys that they're playing with are stimulating. But at the end of the day, when they walk out of that building, what do they carry away in the way of knowledge that they didn't have before? Or is it enough that they just come out thinking science is fun? Is that enough, or are we trying to do something more than that? So let me consider a visit I recently made to the Exploratorium in San Francisco. And I went there because I'm interested in seeing what the designers had in mind when they made a particular piece of apparatus. And I found one interesting toy that I wanted to play with, and it was a challenge. It was presented as a challenge. It's a circular disc, more or less. That's meant to be a circle. And there are a number of magnets at the bottom, and you're instructed to spin the wheel and see what happened to the magnets, see the patterns of what was happening to those magnets as they fell. So I set up the wheel, set it running, and here's a video of what happened when I set that running. Well, it was kind of disappointing that before I'd actually managed to watch it very carefully, that person stepped in front of me and stopped it running. He hadn't read the instructions, he hadn't looked at the information about the experiment, about the apparatus. He'd done nothing at all except come up and stop it. Hands-on experience immediately, but what's going on there? So let me say I set it up again, and here's the video of it with the running for the full time, and see what you think happens to those magnets. I can see there's a kind of pattern of falling as the wheel slows down. Those magnets are falling off the trajectory they're on, and they're falling into some sort of an arc. Let's suppose it's something like a parabola, but I can't actually myself hear what the pattern is. So I was challenged to see the pattern and hear the pattern by the instructions, and I suppose there must be some sort of regularity or irregularity in the way those magnets fall, that they hit the bottom and make some sort of noise. But because of the background noise in the Exploratorium, I couldn't actually make out what the pattern was supposed to be telling me. And I'm not sure exactly what the pattern is either. I'm not sure whether they fall as a parabola. If I just threw things out into the air, if I throw an object out there, I know it travels in a parabola. If I ignore air resistance, a ball that I throw into the air will travel in a parabola. That I understand, but there's a lot that's very complicated going on here. I'm not sure that the fact that they are magnets is crucially important, except that the magnetism will pull them onto the steel plate. They'll be fastened onto the steel plate to some extent. There'll be friction between the plate and the magnet as the magnet moves across the plate. There'll be, whatever you like to call it, centripetal force, the force needed to hold those magnets travelling in a circle. If the wheel is travelling very fast, the magnets will stay at the outside rim of the wheel, just as if you were in a roller coaster. If you go over a loop fast enough, you can go right over the loop without falling off, because the force required to keep you held into that circle will be more than be the weight of gravity. The force required to keep you travelling in that arc will be more than the weight, and so effectively the magnets will be held to the top of that circle. As it slows down, there will become a point when they start to drift away from the edge as the wheel starts to slow down. But it's a very complicated pattern of forces that's involved here, and what is a child supposed to make of this in terms of understanding the science involved? And here's the problem for me with Exploratoria, that you look at the apparatus and you presume, I presume, that the person who designed the apparatus is designing it to demonstrate some principle of science, some scientific law, some scientific phenomenon that is illustrated by the apparatus. You can see it in some other cases. I think one of the favourite ones that I have is you have something on an axle, 2 bars and a metal ball at each end, and you're invited to spin the dumbbell around its axis, and if the balls are made of steel, it's very heavy, it's got a lot of inertia, it'll be difficult to get it going and it'll be difficult to stop it. Whereas if the balls are made of aluminium, much lighter, it'll be much easier to get it running, easier to get it started, easier to get stopping. And if you've got 2 of those, one with steel and one with aluminium, you can conduct a simple experiment to show that, or to experience what it's like that this one has a much greater moment of inertia than the other one. But you have to actually do the work yourself to link the theory to the practice. And in the problem with the ever-falling magnets, the question is, what was the theory? I look at it and I think of what possible science could be illustrated, and I'm dumbfounded by the complexity of it. The point about the illustration is that the point about the apparatus is that it should illustrate a simple point, so that it can, the experience of the hands-on of it will be also an understanding of the theory that's driving it, rather than just the mindless winding of handles and pressing of buttons. I simply can't understand what the person who designed the ever-falling magnets at a demonstration was trying to demonstrate. It's like another example I saw, not at the Exploratorium, but in a different science museum. I saw a cylinder which was filled with a very viscous liquid like glycerine, and there was a hand pump to pump bubbles in at the bottom, and you could watch the bubbles. Very pretty. The bubbles rise up and get bigger as the pressure decreases. They come to the surface, but again, incredibly complicated theory. How much do the bubbles expand as they rise, as they get bigger? The viscosity, well, it gets bigger, but it gets smaller in relation to the size of it's just too confusing to work out what the relationship is between the size of the bubble and the speed at which it rises. It's just fun to pump the air in and to watch the bubbles rise. So the question is, what are we supposed to learn from these things in terms of the theory that they illustrate? Or are they supposed to illustrate it? I'm not absolutely sure even now. In the Exploratorium, some of the exhibits had a note on them that said it was designed by the artist in residence. Well, what's an artist in residence doing in a science museum or Exploratorium? Shouldn't it be a scientist in residence who's designing this to make some aspect of the theory clear? Well, maybe it's just meant to be a puzzle. I'm not telling you this simply because I want to talk about science museums, interesting though that is. There's something here about the relationship between the theory we have, the theories we hold, and what we experience. And what makes these demonstrations in the Science Museum interesting to me is that they're applications of a scientific principle, application of the idea of moment of inertia and mass, application of I'm not sure what, something about magnets, friction and motion in a circle, something about Stokes' law, pressure and volume in different pressures. I don't know. The problem is theory should be able to simplify the phenomena that we see in front of us. And the point of learning science is to try and separate out a single principle and to illustrate it clearly so that when you've got circumstances where there are 3 or 4 or 5 different principles all applying simultaneously, you can start to see and make sense out of what's in front of you. The difficulty is that with children who haven't studied science, they don't have those simple cases at the front of their mind to be able to separate out. So what can they do? They press the buttons, they wind the handles, and don't learn very much at all. Occasionally in the science museums you'll see a conscientious parent leading their child around and explaining exactly what's supposed to be learned from each demonstration. But it's hard work. It's hard work for the parent and it's hard work for the child. And you wonder whether it's really is a better way of learning science than sitting in a classroom, having a teacher give you an introduction to the theory so that you can start to understand what you're looking at. And that's the problem. It's all very well winding the handle, pressing the buttons and having fun, but what are you looking at? Are you paying attention to the right feature that you should be looking at? And there's a tendency, in my view, to rush towards the hands-on, to present science as purely empirical. We are moving towards the naive empiricism in science museums. If you get your hands on the apparatus, you'll learn something. We're also getting in towards naive empiricism, in my view, in much of the research we do in education. What's the answer to the issue that we're looking at? I'll interview some people. Naive empiricism, to my way of thinking, doesn't help us get to the bottom of what's going on. If you've got a very simple model, like moment of inertia, as illustrated by apparatus designed to illustrate it. That's helpful. If you've got an apparatus that's complex, it doesn't help you if you can't apply a theory to it. And I'm afraid that what we're losing from much of the discovery learning and much of the research that we're doing is a sense that theory is necessary in order to make what we're looking at intelligible. So this is a plea, really, for the place of theory, an important place of theory, not an overriding place of theory. Getting your hands on and doing the experiments is important. Collecting data and making sure that you're describing the world that you do encounter is important. But there's also a central place for theory alongside the hands-on. And that's all I would want to say, particularly about my visit to the Exploratorium in San Francisco.